All right, good morning. Good afternoon, everyone. Welcome. I hope you had a good weekend. It's sure good to see you. Love seeing all your faces on my monitor. So if you guys can remember to turn on your cameras, those of you that haven't, I'd really appreciate it. It helps me to have some feedback and all that kind of stuff. So anyway, it is great to see you. I hope you're all doing well and are surviving. This is kind of the push time of the semester. We're kind of in the home stretch, really. We got we got two more exams to go, I guess, and the final. But we're getting through the material, and you guys are doing great. So thank you for your hard work, and thank you for your effort, and thank you for being here. A couple of quick announcements. One is, if you haven't done so, please fill out the instructor evaluation survey. When I looked at my surveys, it says that only about 15% of you have filled it out. It is a little confusing because you may get more than one survey for this class, because you'll get a survey for me and then maybe for the lab instructors, and maybe you got those first and filled those out. But anyway, an easy way to access those surveys is just to go to our homepage in Canvas. So I'll show you here, go to our homepage in Canvas, and right here at the bottom left, it says Student Evaluation of Instructor. You can click there, and you should be able to find the survey and fill it out, okay? So I'd really appreciate you doing that. The other thing I wanted to mention really quick is if you are, over the weekend, there was a little bit of a problem with Pearson's server went down before the problem set was due, and some of you had kind of put it off to the last hour, and so I ended up extending the problem set. Sometimes when I do that in mastering, it doesn't always update in Canvas right away. All right, so it may show it closed in Canvas when in fact I've changed the due date. So the way to access it, because you can always access your assignments here, right, directly on Canvas. But if you go to My Lab and Mastering, and if you go here, open My Lab and Mastering, right, then you can, oh, well, why am I getting this? Oh, because I'm on the student. Sorry, I'm on the student one. It's not showing it. I have to get off the student one. Leave student view. If you go to open My Lab and Mastering, you should be able to see the assignments in there, and you should be able to click on them from there, and that'll have the most up-to-date due date. All right. And also, I've noticed some of you will worry that you started the assignment, and then you came back to it later, and then you finished it, and your grade in Canvas is different than what you expected. That's because, again, Mastering and Canvas got to talk to each other, and sometimes that takes up to 24 hours to update. All right. But you can access all the assignments from here, either from this list or from the calendar. Right. The calendar is kind of nice because it shows you exactly when everything's due. Wait for that to load. So, for example, I ended up changing this assignment to be due tonight just simply because there was some confusion about it. This is the assignment that was due on Friday, okay? But in case you got confused or whatever, or you had problems with the Pearson server, you can actually still finish it up to tonight at midnight without any penalty, okay?
Sometimes if I'm trying to access a page on Pearson, it won't load, and in the navigation window it will say the normal navigation name, and it'll like switch to like the window pop-up window is blocked. Then I'll have to click on it, and then like a very small sub window will pop up, and then I have to reload it again, and then it'll eventually come up without making a new tab. And it's kind of strange, but I don't really know what the cause of that is exactly.
That's kind of weird. It may be, do you have that page that does for your browser checkup? It may be an issue with your browser. If you send me an email, I'll send you the link to the browser checkup, and you can go through your browser and make sure your browser's set up correctly for mastering.
I can show you. I can send you maybe a screen recording next time it happens, so you see what it looks like.
Perfect. That'd be great. Okay, good. Any other questions before we get going here today? Okay. Let's start where we left off last time. And at the end of last time, kind of in a little bit of a rush, we went over delta H relationships. So let me just start this. So just real briefly, remember that when a reaction is multiplied by a factor, delta H reaction should be multiplied by that factor. All right. So if you have a reaction A goes to B, and you know delta H for that reaction, and you multiply that by 2, so you make a 2A goes to 2B, then delta H for that doubled reaction is just twice delta H of the reaction without the doubling, okay? If a reaction is reversed, then delta H changes sign. So if you know delta H for the forward reaction, then delta H for the reverse reaction is just minus delta H for the forward reaction, all right? And then if the reaction can be expressed as a series of steps, delta H for the overall reaction is the sum of the delta H's for the steps. All right. Everybody remember that from last time? And then we had an example that we were working on that got a little bit confused. So let me do this one for you. And what I'll do, I think, is maybe I'll give you a chance to try to set it up, see if you can do it. And I'll chime in here in a couple minutes and guide you through it. But I'd like you to try first. So I'm going to set this up as a poll. I'm going to launch the polling and go ahead and try to work this problem, see if you can do it. And I'll chime in here in a couple minutes and help you out. But it's good for you to just kind of think about it. What would you do? The idea is you got to take these two reactions and figure out what you got to do to them so that they would add up to this reaction, right? Because if you can do that, then you can use the delta H's and sum them together to get delta H for this. Okay, that's the idea. If you're struggling, I'll give you a quick hint. Notice that on the left side of this reaction, you have 1/2 N2 and 1/2 O2. But on the right side of the reaction that you want, you have N2 and O2, right? So what might you do to this reaction so you get N2 and O2 as products, and instead of having 1/2s on there, you have 1s? Okay, so for the first reaction, what you got to do is you got to reverse it and multiply it by 2, right? So when you reverse it and multiply it by 2, it becomes 2NO goes to N2 plus O2. And then delta H for that reaction becomes twice the negative of delta H for the forward reaction, right? So delta H becomes that. All right, now concentrate on the second reaction. What do you have to do to the second reaction? Notice you have NOCl here as a product, but what do you have in the target reaction? 2NOCl as a reactant. So what might you do to this reaction?
That one has to be reversed, correct?
Yeah, it also has to be reversed. And in this case, by coincidence, it also has to be multiplied by 2. Okay, so what you have here is when you reverse this one and multiply it by 2, right? You get 2NOCl goes to 2NO plus Cl2, and then delta H2 for that is again twice the negative of delta H for the forward reaction. So you get 77.2 kilojoules. Now notice when you add these two reactions together, right? You got 2NO here and you got 2NO there, right? So those cancel out, and you're left with 2NOCl, sorry, not plus, goes to N2 plus O2 plus Cl2. Aha, that's the target reaction that you're trying to get delta H for, right? And delta H for that reaction then is going to be the sum of delta H1 plus delta H2, which is equal to negative 180.6 kilojoules plus, sorry, there shouldn't be any per mole there, plus 77.2 kilojoules, and that ends up being negative 103.4 kilojoules. So the correct answer for that is C, right? Does that make sense, everyone? Awesome. Okay. Questions? Any questions on that? All right. Very good. Very good. Very good. Very good. I'm going to stop the poll. All right. So now what you want to, then our next goal then, so this is one way to find delta H for a reaction. So if we want to find delta H for a reaction and we can get that reaction to be the sum of two other reactions whose delta H is we know, right? Then we can get delta H for that reaction. But that's not a very general way to get delta H, okay? So now we're going to look at a more general way to get delta H, and that's from tabulated standard enthalpies of formation, all right? And the idea here is simply this. Remember when we talked about our mountain climbing analogy, right? If you start at 10,000 feet, if you start at 5,000 feet and you climb at 10,000 feet and you want to know how far you climb, you just subtract your final altitude from your initial altitude, right? So if you start at 5,000, you climb at 10,000, you'd say, aha, I climbed 10,000 minus 5,000 equals 5,000 feet, right? It's your final minus initial. So similarly, you should be able to get, if you have a reaction A plus 2B goes to C, because enthalpy is a state function, right? It depends only on the state of the system and not on how it got there. In other words, because enthalpy is kind of like altitude, all right? Then delta H would just be the enthalpy of C, right? Minus the enthalpy of A plus twice the enthalpy of B, right? So if you knew the enthalpy of these individual things, right, you can get the change in enthalpy simply by subtracting the enthalpy of the product times its stoichiometric coefficient minus the enthalpies of the reactants times their stoichiometric coefficients, right? And that would give you delta H for that reaction, Okay, if you knew those values. Well, the question is, how do you know those values? Well, it turns out they're tabulated, all right? But there's a little bit of a trick, because this isn't that difficult in terms of the implementation of this idea, but conceptually it can be a little bit confusing. Just like altitude, right? Just like altitude, for enthalpy, just like for altitude, we assign sea level, right? So for enthalpy, we got to do the same thing, all right? So, for example, we say that, you know, a particular mountain is, you know, Mount Pinos, Pine Mountain back here, maybe is at 6,000 feet, right? That's relative to some standard, right? What's the standard we use? Sea level. Notice that, given that standard, we have some negative altitudes, right? In Death Valley, there are some altitudes that are less than 0, right? But you got to assign some standard. You got to assign some sea level, all right? So in order to be able to carry this out, in order to be able to assign these enthalpies, we have to assign 0 to something. Okay, we got to assign, in other words, we got to figure out what sea level is, all right? So for enthalpy, sea level is pure elements in their standard states. Pure elements in their standard states are sea level. What is a standard state? A standard state for a gas is a pure gas at 1 atmosphere. A standard state for a liquid or solid is a pure solid or liquid in its most stable form at 1 atmosphere pressure and the temperature of interest, which is usually taken to be 25 degrees. For a substance in solution, the standard state is a concentration of 1 molar. Okay? Again, what are we doing here? We're just defining sea level. All right? And then we define the standard enthalpy change as the change in enthalpy when all the reactants and products are in their standard states. Right? So this is going to be the standard enthalpy change. It says, look, when everything is in its standard state, then delta H is equal to the change in enthalpy, right? And that's what this little 0 there means. It means standard state, when everything is in its standard state. And then lastly, we define the standard enthalpy of formation as the enthalpy change for a reaction when you have the pure elements forming the pure compound. Okay? And that's called the heat of formation. So what that does is it measures how far any compound is from sea level, right? Because remember, what do we define as sea level? Pure elements in their standard states, right? So if you form a compound from its pure elements in its standard state, that's kind of a measure of how far away it is from sea level. And so these things are tabulated, right? So here's a table of all the standard enthalpies of formation of different compounds. Notice right away, what do you notice about pure elements? Anybody?
Is always 0?
They're all 0. Why? Because we define it that way, right? We just said pure elements in their standard states are all 0, all right? Second thing, what do you notice about most compounds? Are they above sea level or below sea level?
Below.
Below. Okay. Most compounds are below sea level. That means that when you form those compounds from its elements, energy is given off, right? Because you go from sea level to a lower energy level. And remember, when you go down in energy, just like when I drop a pen, right? If I drop a pen, it goes from higher energy to lower energy, energy is given off, right? So when these compounds are formed from their elements, energy is given off, right? So most compounds lie below sea level, but notice that not all of them do, right? Some compounds lie above sea level, right? These compounds are particularly reactive, it turns out, right? Because they have a lot of potential energy, right? A lot of, well, in this case, enthalpy, but you can kind of think of it as potential energy, okay? So now that we know these, right, we can calculate delta H for any reaction, right? And all we got to do to get it is use this equation. which is essentially the same thing as this, but instead of absolute values of enthalpy like we had here, we're going to use the enthalpies of formation for those substances. Okay? In other words, we're going to use the values in this table and plug them in, right? And then we can find delta H for any reaction. So delta H becomes the sum of the enthalpies of formation of the products, each multiplied by their stoichiometric coefficients, that's what this N is here, minus the sum of the enthalpies of formation of the reactants, each multiplied times its stoichiometric coefficient. And if we do that, we can get delta H for any reaction. Okay? Abe, do you have a quick question?
Yeah, I guess I'm still wondering how exactly, like, how it could be positive that delta H can still be positive for some of the compounds.
Oh yeah, because remember, yes, because some compounds actually, when they form, they absorb energy from their surroundings.
Oh, okay.
Okay, but those kinds of compounds tend to be a little bit unstable and pretty reactive.
Interesting. Okay. Thank you.
Yeah, that's right. Good question. Thank you. All right, so let's do an example. Okay. So we have this equation, this reaction here, right? And we want to figure out delta H for it. All right. So we're going to have to look up these values, right? And I'll put the table back up in a minute, but let me just write this out. It's going to be the sum. It's going to be the sum of the heats of formation of the products, each multiplied by its coefficient, by its stoichiometric coefficient, minus the sum of the heats of formation of the reactants, each multiplied by its coefficient. All right, so let's start with the product. So it's going to be 4 times delta HF for CO2, all right? 4 times the heat of formation of CO2 plus 2 times the heat of formation of H2O. And we got to be a little bit careful here because we got to remember that this is gas and this is gas because the state makes a difference. Okay, so make sure you're careful with the state. Okay, and then we're going to subtract out the sum of the heats of formation of the reactants times their stoichiometric coefficients, right? So 2 times delta HF for C2H2 gas plus 5 times delta HF for O2 gas. All right, so now we can go back to our table and look these things up, right? So it becomes 4 times delta HF for CO2 gas. So here's CO2 gas, right? Minus 393.5 kilojoules. Okay, well, I'm just going to remember that it's kilojoules. And then plus 2 times delta HF for H2O gas. Here's H2O gas, negative 241.8. Right? And then it's going to be minus 2 times delta HF for C2H2 gas, which is right here. So 2 times 227.6, right? And then it's plus 5 times the heat of formation of O2. And here's O2, and what's O2?
0.
0. Why?
Pure element.
Yep, it's pure element, right? So all pure elements are always going to be 0 in this situation. Yeah? Okay, so if you add this all up, and you're careful, you should get negative 2612.8 kilojoules. Does that make sense? You ready to try one yourself? Yep, okay. Try this one. And what I've done is I've put the delta HFs right here so you don't have to look them up in the table. Okay, so try this problem. And I'll start the poll.
Is the O2 not mentioned?
So remember, O2 is a what?
Oh, okay. Never mind.
Wait, Troy, I have a quick question.
Yeah.
So I understand that O2 would just have a change of H of just 0.
Correct.
Is it 0? I understand it's zero because it's a pure element, but is it like did they say like, oh, a pure element will have a change of H as 0 just because it's like so abundant, or is it just because?
Because that's where we define sea level. We said sea level is all the pure elements in their standard states. So just like in altitude, we set sea level to be the mean high tide line.
Yeah.
I mean the mean tide line.
Mhm.
We say, okay, that's 0. We're going to measure all altitudes from that relative to that. For enthalpies, we say, okay, all pure elements are 0, and we're going to measure all changes in enthalpy from those pure elements at 0.
Okay.
All right, try to finish this up in the next 15 seconds or so. Okay, I'm going to end it there. And the right answer is A. And most of you ended up getting that. A few of you didn't. Let's just see really quick. So what you want to do is you want to say delta H, right, for the reaction is equal to 4 times delta HF for CO2, right? It's the products times their stoichiometric coefficients minus the reactants times their stoichiometric coefficients, right? So 4 times CO2, you look up CO2, make sure you have gas, that's correct. So that's 4 times negative 393.5 plus 6 times the value for water. Notice here you got gas and liquid, make sure you use the value for gas, right? So 6 times negative 241.8, right? Minus, in big brackets, 2 times the enthalpy of formation of C2H5OH, liquid, which is negative 277.6, right? Plus 6 times delta HF for oxygen, but that's a pure element in its standard state, so that's 0, okay? And if you add all that up, you should get that that's equal to negative 2470 kilojoules. Does that make sense? So this is a general way you can get delta H from any reaction. This table is in the book, and it's also in the appendix as a more thorough table, okay? So you can find these delta H's either from this table in the book, which is limited, but in the appendix in the book, there's a more complete table, all right? So look for it there as you're working these problems on the problem set, okay? Great, any questions? Yes, on the exam, you won't have to memorize that chart. You'll be given the values that you need, kind of like you were in this problem. Any other questions? Okay, that concludes chapter 7 on thermochemistry. So congratulations, we made it through that, and we're going to now begin a new chapter, chapter 8. Let me just set this up really quick. Okay, so chapter 8, we're going to start talking about quantum mechanics, okay? So at the end of the 1800s, right? The end of the 1800s, physics had kind of reached a plateau. The motion of objects, right? Like particles, motion of particles was very well explained by Newton's equations of motion. Right? And some of you might be familiar with equations like this if you've taken physics, right? Equations like this: x at time t is equal to the initial x plus v times delta t, right? That tells you that if you want to know the position of a particle, this is just for straight line motion, right? All you got to do is know its initial position and its initial velocity, and then you can predict its position anywhere in the future, right? So notice that position velocity, right, lead to a trajectory, right? This equation is deterministic. And at this point in time, physicists had discovered a world that was very deterministic. It kind of worked like a clock, right? Every particle in the universe, right, has a position and velocity right now. So that means if you knew every single position, every single velocity of every single particle in the universe, then the whole future was determined, right? Anything in later on in the future was already predetermined. That, philosophically, that's called determinism. Determinism. What am I doing? I'm spelling that wrong. Determinism. The present determines the future, right? And you guys have all experienced this, right? If you've ever ran after a baseball in the outfield to try to catch it, right? The minute it leaves the bat, or if someone's throwing it, the minute it leaves the hand of the person's throwing it, right? What are you doing in your brain? You're actually using Newton's equations to figure out where that ball is going to land, right? You're estimating, okay, where is it? And what's its velocity? Or more accurately, it would be what's its momentum. You want to know its direction and its velocity, right? But for us, we can just think about, okay, you want to know where it is, and you kind of want to know how fast it's going and which direction it's going, right? That's its momentum. And if you know both of those things, you can predict where it's going to land, right? That's why an outfielder can run and catch a baseball in the outfield, right? Because a baseball behaves deterministically, right? Its position and its velocity determines where it's going to land. Yeah, are you with me? Does that make sense? So those were Newton's equations. Physicists, again, in the late 1800s, planets behave this way, baseballs behave this way, bullets behave this way. We thought electrons behaved this way too, right? We thought the various tiniest particles that compose matter behave this way as well, all right? What we found was, in fact, that was not the case, okay? Electrons do not behave deterministically like this. If you were trying to catch an electron in the outfield, you'd have no way of being able to watch it and say, I can see its position and its velocity, and therefore I know where it's going to land, okay? Electrons do not behave this way. So we want to understand how electrons behave. The second part of this is that while the motion of particles was determined by Newton's equations, the behavior of light was determined by Maxwell's equations. All right? And light was a wave phenomenon, right? So light behaved like a wave. And of course, things like baseballs and planets behave like particles. But when applied to, when we started looking more carefully at light and electrons, we found that, in fact, light has some particle properties. A particle of light has a name. Does anyone know what a particle of light is called?
A photon?
A photon. So light was thought to be a wave phenomenon, but then discovered that it was also composed of particles. And then electrons were thought to be particles, but then we discovered that they have a wave property as well, right? So there became a blurring of the lines here between what we thought of at the end of the 1800s, okay? And it wasn't super comfortable for a lot of physicists. I'll get back to this in a minute. Niels Bohr, who was one of the founders of quantum mechanics, said anyone who is not shocked by quantum mechanics has not understood it. Erwin Schrödinger, who has a famous equation named after him called the Schrödinger equation that lies at the heart of quantum mechanics, said, I don't like it, and I'm sorry I ever had anything to do with it. And Albert Einstein, who also had a role in the development of quantum mechanics, refused to believe that it was true. He refused to accept the theory. And he said, it can't be true because God does not play dice with the universe, right? And so this was the revolution that happened in the early 1900s, the revolution that we now call quantum mechanics, that is now the basis of the periodic table. It's the basis of, it's the theory that explains the periodic law and the periodic table. It's the theory that explains the operations of lasers and diodes. It's at the heart of chemistry and physics, right? And today, even though these scientists were not very comfortable with it, it's the bedrock theory, really, for these small particles and the way they behave, all right? And so that's the theory we want to try to understand, all right? And from our point of view, why are we interested in this? We're interested in it because ultimately, chemistry is based on electron behavior, right? We said that, what is a chemical bond? It's the sharing or transfer of electrons, right? And electrons behave quantum mechanically. So if we want to understand chemistry, we must understand quantum mechanics, all right? So what I'd like to do is just talk a little bit about this. You guys may have heard of the Schrodinger's cat thing. We'll talk about that for a little bit. And then we'll start looking at light and the behavior of light, because we need to understand light a little bit. And then what I want to do is walk you through an experiment, probably won't get to this till next time, called the double slit experiment. And the double slit experiment kind of shows you how these electrons behave. And it kind of shows you the very core of quantum mechanics, and it shows you things like the wave particle duality of matter, and it shows you the uncertainty principle, and these principles are really at the heart of quantum mechanics. So that's where we're going here in this chapter. And then we'll apply quantum mechanics to the hydrogen atom and learn about orbitals, and then we're going to bring it all around, and we're going to see how all this explains the periodic law and the organization of the periodic table that we just learned about. Okay, so that's kind of the idea. All right, but a little bit about Schrodinger's cat. So in 1935, Schrodinger wrote this paper in which he talked about this cat that was in this box. And what he was addressing was the idea that in quantum mechanics, an unobserved system can be in two states at the same time, which seems really weird, right? Like, for example, there's a phenomenon known as radioactive decay. Radioactive decay is when an atom loses a piece of its nucleus and it spits out a piece of its nucleus as an energetic particle, okay? That's called nuclear decay. So in quantum mechanics, because a particle or a system can be in two states at once, an atom can be in the state of both having spit out a particle and not having spit out the particle at the same time. And we actually describe it that way with equations that give not whether or not the particle was spit out, but the probability of, when observed, will you find that it spit out the particle or not, okay? Because the idea in quantum mechanics is that this unobserved system can sort of be in what's called a superposition of two states. And it's only when you observe it that you collapse the superposition and cause it to be in one state or the other. So Einstein was trying to explain this with this cat experiment. So here's the idea. You have this cat, you put it in a box, and then you have a sample of radioactive matter that, if it decays, it sets off a mechanism that causes a hammer to break a beaker that then releases a poison that causes the cat to die. All right? And for a certain amount of time, there's exactly a 50% chance that this atom in this nuclear radioactive atom will decay. All right? But so you put everything in the box, you shut it off, and you don't observe it. Unobserved, that atom can be in a superposition of those two states, both decayed and undecayed, which means then that the cat could be in this superposition of states, both dead and undead at the same time. Okay? And only when you open the box and observe it do you force it into one state or the other. Okay? Now, it turns out that for the cat, that really doesn't happen, because the quantum effects don't really translate into the macro world like that, okay? Because essentially the cat becomes the observer, right? But the idea is actually valid, right? The idea that something can be in two states at the same time when it's unobserved, and then when you observe it, it collapses into one state. That's called the superposition principle in quantum mechanics, all right? And we're going to see that principle at work in this double slit experiment when we get to it, okay? Let me pause and see if you have any questions.
I just have something comes to mind about the element of observation concerning that experiment.
Yes.
What does that say about particles or dark matter in relation to, observation affecting its state?
Exactly right. And that's a huge part of quantum mechanics, right? Observation affects the outcome of an experiment. And why is that? If you think about, observing a baseball, right? How do you observe a baseball? There are photons bouncing off the baseball that eventually bounce back to your eye, and you can track the baseball that way, right? The position and the momentum of the baseball is not affected by those tiny photons bouncing off it because the baseball is so big. But when you get down to the quantum level, when you get to the level of particles that are so small that there are no smaller particles in existence, you no longer have that option, right? Of trying to observe it with something even smaller. Why don't you have that option? Because nothing smaller exists. Yeah? So when you make an observation, you affect the outcome. And we'll see that in the double slit experiment very, very clearly. Okay? Does that make sense? Great question, Michael.
Fascinating. Thank you.
Yeah. Other questions? Abe?
When did this class turn into a physics class? Just curious.
When we decided to try to understand atoms and chemical bonding. Right? Because, at the end of the day, electrons are particles and we got to understand their behavior. But yeah, I get what you're saying. There's a chemistry, a lot of chemistry is based on physics, right? Because physics governs how these small particles behave. And if we want to understand chemistry, we really got to understand quantum mechanics. So
Go hand in hand, sort of, right?
yeah, we go hand in hand. Yep. What else? Other
You
questions?
can't go with one without going with the other one.
That's correct. Although, chemistry is the more interesting one of the two because all the important problems in physics lie right in the middle in chemistry. And so that's why chemistry answers some, with physics, the kinds of questions that you ask are very well controlled experiment. I like physics a lot. I'm just kidding around to some degree. But, and I'm a physical chemist, so I'm kind of at the border between physics and chemistry anyway, in terms of my own field. But I love the questions in chemistry just because it's complex enough that you can look at very complex systems. In fact, you can look at things like, DNA and proteins and very complicated systems that really have effects in the real world. And yet you can approach those from a very physical point of view, right? Having physics as a guide. So it's really a beautiful thing.
For the record, I didn't even take physics yet, and I still passed an astrophysics course.
Nice.
So yeah.
Very, very good. Okay, any other questions before we move on? Because we're going to start looking at light next. All right, so let's talk a little bit about the nature of light. Again, before quantum mechanics, light was thought to be purely a wave phenomenon. And so the way we think of light as a wave is that there's an electric field that oscillates in space. Okay? What's an electric field? An electric field is an area around a charged particle where forces are experienced. All right? So, for example, if you walk across a carpet on a dry day and you acquire extra electrons, because you've rubbed them off the carpet and they've gone into your body, you might notice that your hair stands on end a little bit, right? That's because there's a force experienced by the electric field caused by the extra charged particles that you've acquired, all right? So you have a little electric field around you at that point. Usually when you touch something metal, you know, the electrons drain back out and go back to ground. And sometimes you get a little shocked because of that. But that's what an electric field is. It's an area where charged particles experience a force, okay? And it turns out that a changing electric field induces a magnetic field. And you know this, for example, if you've ever made an electromagnet, right? I was kind of a nerdy kid, so I would like take batteries and wires and I'd hook them up and wind the wire around a nail or something like that, right? And then when you hook up the battery, right, the nail becomes magnetic, right? It becomes an electromagnet. That's because a changing electrical current, a moving electrical current generates a magnetic field, okay? And so you have the electric field oscillating in space, generating this magnetic field, which also oscillates in space. And actually, they induce each other. So the energy kind of sloshes back and forth between the electric field and magnetic field because a changing magnetic field, turns out, induces an electric field, which is why a generator works, right? A generator, you have magnets that are moving, and those moving magnets in a magnetic field generate an electric field, okay? So anyway, you don't have to understand all that. Just know that you have an electric field that oscillates and a magnetic field that oscillates basically perpendicular to that, okay? Light travels at 3.00 times 10 to the 8th meters per second. That's a constant. It's called the speed of light, right? And that's pretty fast. That's 186,000 miles per second. And just to get a feeling for that, if you created a flash of light at the equator and forced it to travel all the way around the world, it would come back to you in 1/7 of a second. All right, it would travel all the way around the equator. All right, so it's very, very fast. Light travels very, very fast. You notice this because light travels much quicker than sound, for example. So light travels at this velocity, sound travels at 340 meters per second. So when you see a crack of thunder in the sky, when you see a bolt of lightning in the sky, the light reaches your eye almost instantaneously, but the sound takes 340 meters per second. So you usually see the flash and then you hear the thunder, right? Because of the delay. That's why all these, space movies where things blow up in outer space and you see the explosion and hear the sound at the same time, they're all wrong, right? That never happens. And in fact, if you're really in outer space and there's no air to carry the sound, then there is no sound either. So double trouble. But it wouldn't be really as exciting to see Star Wars, shoot up another ship and then not be able to hear anything, right? So, or to have a delay, right? So anyway, but there's where you see the fast speed of sound. Two very important characteristics about the wave. The first one is lambda, which is called the wavelength. And it's basically the distance between two equal parts of the wave. Usually it's taken as the distance between peaks, okay? Distance between peaks in the wave, all right? And then you got the amplitude, which is the height of the peak. Okay, so this is the amplitude, that's the wavelength. For visible light, wavelength determines color. Right? So red light, turns out, has a longer wavelength than yellow light. Yellow light has a longer wavelength than blue light. Okay? So wavelength determines color. Amplitude determines brightness. So a really bright red light has the wavelength of red light, but then it's very, very high amplitude, right? That's why it looks bright, okay? If it's dim, that means it has a lower amplitude. So the amplitude can change independent of the wavelength, right? So you can have a bright red light or a dim red light, and the difference is not the wavelength, but the amplitude. Does that make sense? So white light contains all of the colors of light that we can see, all the visible colors, all right? And you can see this when you pass it through a prism, right? Or I don't know if you remember the colors of the rainbow, right? Red, orange, yellow, green, blue, indigo, and violet, they're all contained. That's because white light contains all these different wavelengths together, but a prism can spread out those wavelengths in space so you can see them individually, okay? The reason an object appears a particular color is because white light bounces off of it, and molecules, like for example, in this woman's red shirt, the molecules in the shirt are going to absorb all of that light except for red. And the red light is reflected or scattered, and so you see the red light, and that makes the shirt appear red, right? That's because it's absorbing all these other colors except for red. I also wanted to find the frequency of light, which is the number of cycles that pass through a point in 1 second, right? So in other words, if you're standing right here and this light's going by, how many cycles? What's a cycle? A complete cycle. So it can be from 0 to 0, or from peak to peak, or from trough to trough, right? This is the peak, this is the trough, okay? So frequency is how many of these cycles pass through a given point in a second. And frequency is related to both the wavelength and the speed of light. So the frequency is equal to c over lambda. All right? The frequency is equal to the wave of light. Notice what you have here, meters per second divided by meters. The meters cancel and you get 1 over seconds. That unit is often called a hertz. A hertz is equal to just 1 over second. All right, so let's calculate the frequency of light with a wavelength of 1 meter. All right, so we can just plug it into here. Nu is equal to 3.00 times 10 to the 8th meters per second divided by 1 meter, right? And that comes out to be equal to 3.00 times 10 to the 8th hertz, or 3.00 times 10 to the 8th over seconds, all right? Units of frequency. Let's see. Questions? Does this make sense?
Yeah, I have a question.
Yeah.
What is symbol we use for help?
Oh, Javier, for some reason, every time your audio is so garbled, can you just type your question in the text, please?
Yeah.
Yeah, sorry. It's just very hard to understand your audio for some reason. Okay, while he's asking the question, what is the symbol used for hertz? Oh, it's just HZ, hertz. That's the abbreviation. 1 HZ is equal to 1 hertz is equal to 1 over seconds. Okay, go ahead and try this one yourself. So here, I asked you to find frequency given wavelength. In this problem, I'm asking you to find wavelength given frequency. Okay, but you're still going to use the same equation. Okay, looking good. About 10 more seconds and I'm gonna end it. 10 more seconds. Okay, the right answer is B, right? So most of you got that. Good job. You're basically going to use the same equation, but you're just going to solve for lambda, right? So you're going to say lambda is equal to C over nu, right? So that's 3.00 times 10 to the 8th meters per second divided by 2.3 times 10 to the 12th over seconds, right? And that gives you 1.3 times 10 to the minus 4 meters. Okay. So that's how you do that. Okay, good. Any questions? It's all making sense?
Which one's new again?
Nu is the frequency.
Which symbol is that?
Oh, right here.
Okay.
It kind of looks like a V. So a V is like this, a nu is like that.
So that's for, what was it?
Frequency.
Okay.
Frequency in hertz. Okay? So that, yeah, that stands for frequency.
Use your constant, right?
C is the constant. 3 times 10 to the 8th meters per second. Yep, speed of light. So a good way to remember that is we had a joke in shows you how nerdy I was in graduate school. We'd always go around and ask each other, "Hey, what's new?" You know, so whenever anybody asked you what's new, you'd answer C over lambda. Get it? What's new? C over lambda. I know, it's pretty bad. All right. That's what happens when you spend a lot of time in the lab. You just like to try to entertain yourself any way you can, even like stupid jokes like that. Okay, electromagnetic spectrum. Let's jump into that for a minute. Because light is electric field and magnetic field, it's known as electromagnetic radiation. Is just a broad term, right? And the entire spectrum of electromagnetic radiation is much broader and contains a lot more wavelengths than what our eyes can see. Okay, so our eyes can only see a sort of tiny portion right here in the middle of the entire electromagnetic spectrum. So here I plot frequency from low frequency to high frequency, or wavelength from long wavelength to short wavelength. Okay, I kind of like to think in wavelength, but it doesn't matter. You can think of them either way. You know one, you know the other, right? Because what's new? C over lambda, right? So if you know nu, you know lambda. If you know lambda, you know nu, right? You know both of them. So over here on the long wavelength side, you got wavelengths the size of football fields or bigger. Okay, 10 meters, 10 to the 3rd meters, 10 to the 5th meters. And over here, you got wavelengths so small that you can barely even imagine it, 10 to the minus 15 meters. All right, so this is the whole range of possible wavelengths for electromagnetic radiation. All right. And what we can see is a little sliver here in the middle that goes from 750 nanometers. Okay, remember nano is 10 to the minus 9. 750 nanometers to 400 nanometers. All right, so it's really just a tiny sliver that our eyes can see. Unless you're Geordi from Star Trek and you wear that, you have that cool visor. You guys ever see Star Trek Next Generation? And Geordi has this visor, and that visor allows him to see other wavelengths because he's blind. But when he wears his visor, he can see visible light, but he can also see ultraviolet and infrared, and so all these other wavelengths as well. And of course, the first question you ask yourself is, well, what color is ultraviolet light? Well, I don't know the answer to that question, right? Because we know what violet light looks like, but the next wavelength over we can't see. So That would be, if I could ever see another wavelength of light, the first thing I'd want to know is what color was it? Because it'd be a different color than the ones we can see, right? Isn't that weird to think about? But anyway, all right. So let's go through and go on either side of this and understand a little bit about these different wavelengths ranges. So just to the longer wavelength side of visible light is infrared light, okay? Infrared light is not visible to our eyes, but you can measure it with certain cameras. So certain cameras are sensitive to infrared light. Of course, infrared light is not really this color because we can't see infrared light. So what we're seeing here is basically a false color image, right? Where we put visible color on top of the infrared light. But infrared light is given off by all things based on their temperature. And the hotter something is, the more infrared light it gives off and the shorter the wavelength of that light, all right? And so you can kind of see that here. Look at this dog. He has a very nice winter coat, right? Because you can't see the heat of this dog's body through the coat, right? You can see heat coming out through his mouth and a little bit here on his ears and his eyes, but you do notice, what do you notice about his nose?
It's cold.
It's cold, yeah.
Which, you know, that's what they say, a healthy dog should have a cold nose, right? Isn't that, have you heard that? Anyway, so infrared light is the basis for all night vision, right? So any night vision kind of operations that you have on airplanes or in military equipment, right? They're detecting infrared light. Wavelengths, you know, range from about 10 to the -3 to 10 to the -6 meters, right? Shorter wavelengths, longer wavelengths than infrared, you got the microwave region, all right? These are wavelengths of about a centimeter, about this long, okay? Of course, there's a range 10 to the -1 and 10 to the -3. Microwave radiation happens to have the same frequency as the frequency at which water molecules naturally rotate due to thermal energy. So water molecules will rotate as they get warmed up, and the microwave frequency happens to be at the same frequency of that rotation, which means that microwaves are very good at causing molecules to rotate even faster, right? Which is why we have microwave ovens and why they work. When you put water in a microwave oven, the microwave radiation causes the water molecules to rotate faster and faster and faster, and that causes the food to heat up, right? Things that don't contain water typically don't get warm in a microwave because microwave is very specific to water. The long wavelength end of microwaves is also used for telephone communication. So your cell phone is using microwave radiation in this region for communication. Longer wavelengths yet, you got radio waves, right? Which include all of these wavelengths here, very, very long wavelengths. They're used for all different kinds of communication. FM signal, for example, for radio, AM signal, TV, and also some cell phone communications. All right. If you go to shorter wavelengths than visible, I want to reveal something here that we'll get to more in a minute, but as you move this way on the spectrum, we haven't introduced the particle nature of light yet, but a particle of light is called a photon. And as you go towards shorter and shorter wavelengths, the energy of a photon gets bigger and bigger, okay? So you can think of light as particles, and the energy of a particle depends on the wavelength of the light. The shorter the wavelength, the higher the energy. And we'll look at that again more carefully in a minute, but I just want you to understand that as we go through here. Because it turns out that photons in this region do not have enough energy to break a chemical bond, all right? It's right in the visible region where photons begin to have enough energy to break chemical bonds, which is why we can see visible light, because what it does is it breaks a chemical bond in a molecule in our eye, and it's a double bond. So it causes, what happens is that you have like a bond like this, and you have a molecule, let's say it looks like this. See, can you see me? Is that better maybe? No, this is better. The light will break this one bond and it'll cause the molecule to isomerize. It'll cause it to flip. And that's what causes a nerve signal to be sent up to your brain that then results in vision, okay? So that's why light of longer wavelengths won't cause that bond to break, right? It doesn't have enough energy in the photon, all right? And light that is shorter wavelength has too much energy, right? And in fact can actually damage molecules in your eye because it can cause bonds to break permanently, right? That's why you don't want to stare at ultraviolet light. Ultraviolet light has much more energy per photon, and it has the ability to break chemical bonds. And in fact, that's what's responsible for a sunburn, right? If you're out in the sun too long, some of the UV light will damage molecules in your skin that then results in a sunburn, okay? So that's ultraviolet light. Shorter wavelengths yet, we get to X-rays. This kind of electromagnetic radiation can penetrate through many objects. It can penetrate right through your skin, right? And it can be used to image internal structures in our bodies, like bones, for example, right? If you've broken a bone, you might have had an X-ray to determine what bone was broken and whether or not it was broken. It also can be used to create images, right? And so X-rays are very useful from a medical point of view. Again, they have very, very short wavelengths, right? Which means that they have a lot of energy per photon, which means they can also damage biological molecules, right? So you don't want to expose yourself needlessly to X-rays, right? A small amount is not really harmful, but large amounts can be harmful. Shorter wavelengths yet, you have the kind of radiation that's given off by nuclear processes called gamma radiation. Very, very short wavelength, very, very high energy per photon. Exposure to this can also can damage biological molecules. So again, we want to limit, generally we want to limit our exposure to ultraviolet, X-ray, and gamma rays, right? Anything down here is fine. But these can damage biological molecules. And by the way, the kind of molecules that are susceptible to damage and that end up with consequences are DNA, right? So when the DNA of a cell is damaged either by ultraviolet, X-ray, or gamma ray radiation, that DNA, when it's damaged, it usually means that the cell can no longer reproduce. And once a cell can no longer reproduce, it usually dies, all right? So you can get damage, you can kill cells with these kinds of radiation. However, sometimes when this kind of radiation interacts with the DNA of a cell, it alters the DNA in such a way that doesn't end up killing the cell, but rather causes the cell to divide abnormally, right? So when you change the DNA in those ways, the cell can divide abnormally, and that can then lead to cancer, right? So that's why exposure to all these kinds of radiation in excess can increase cancer risk, for example. Okay. Questions about the electromagnetic spectrum or anything else? Did I see a question on the chat? Colorblind people are blind to certain wavelengths. They can't tell the difference between certain wavelengths. Basically, they look the same color to them. Let's see, Skylar.
I know some animals can see just like a bigger range of colors than humans can, and I was wondering if you knew how that worked.
Well, I know there's some animals that can that see through other mechanisms. For example, like a bat sees not through light but through sound waves. So they can form an image out of sound waves, which is kind of like what happens with an ultrasound. Have you ever seen a doctor use an ultrasound, like for example, to get an image of a developing baby, right? A lot of times you can get a little face shot of your baby before it's born, right? And that's done with ultrasound, which uses sound to create images. And so bats, for example, can do that. I am not totally familiar. I'm not sure what animals can actually see other wavelengths beyond the visible.
I looked it up and it's the mantis shrimp. It says that it has 16 color receptive cones and can detect 10 times more color than a human.
So can it see wavelengths outside of the visible range?
I'm not sure.
Yeah.
Yes.
Yeah, it can. Okay. Yeah. So, I'm guessing it has a different mechanism in the eye that responds to those different wavelengths and then can see them. Let's see. Other questions? Alex, did you have a question?
Yeah, I had a question and a couple of comments. So the question is, for infrared light, is it like cold, or is it like either cold to the coolest to the hottest, or vice versa, like as you go down the spectrum?
So everything that has a finite temperature actually emits electromagnetic radiation. As the object gets hotter and hotter, it emits more of that radiation and shorter wavelength radiation. So for example, our bodies, because of their temperature, they kind of glow like a light bulb in the infrared. We're giving off all this infrared radiation, right? If you get something hotter, it'll give out even more radiation, and that radiation will shift to shorter wavelength.
Okay.
Function of temperature.
Because I was thinking in terms of like astronomy, like usually stars I think that are red are like the coolest.
Correct.
And then, like the blue ones, they're hottest.
Correct. Because as things get hotter, they emit shorter and shorter wavelengths.
So I assumed from that picture that the blue color was like the hottest.
Correct.
Okay.
Correct.
And I was also going to say that it's like, I mean, we normally consider ourselves like, being able to see pretty well, and then they're like, compared to people who are blind, I can't see at all. But like realistically, like aren't we all blind for the most part? Like we can see hardly anything compared to what there is.
Yeah, that's good. I like that. Let's see, one last question, then I have to end class. Taylor.
So these are just the limits, and if you go, like if we're at gamma rays and then let's say you pump even more energy, you just make more gamma rays.
Yeah, you just get shorter and shorter wavelength of gamma.
Okay.
But
It's just never, that's like the limits though.
yeah, I mean, this goes really infinite in both directions. But you get to a point where, it's so much energy that it's not very common, right?
Okay.
So it really goes to infinity. I mean, you can keep making, at least theoretically, you can keep making higher and higher energy photons, but there just aren't any.
Okay.
Oh,
Okay. That makes sense.
And similarly with the wavelength, it gets so long that it almost becomes just a flat curve.
Okay. Because we don't see gamma rays very often, I would imagine.
There are gamma rays. The Earth is constantly bombarded with gamma rays that come from the sun. But our atmosphere filters most of that out. So most of our exposure to gamma rays comes from radioactive substances that are in the ground. So for example, the ground below us, probably below all of us right now, contains small amounts of uranium. And the uranium, as it decays, will spit out some gamma rays. So we're constantly exposed to these things. We're just exposed in small amounts. And in small amounts, it's not very harmful.
Okay. Thank you.
Yep, good. Okay, I'm going to go ahead and officially end class here. I'd like to thank you all for your attention, and I hope you have a wonderful day. I will, of course, stay on and answer any other questions you might have, but I'm going to stop the recording here. And thank you for coming. If you're not going to hang around for questions, I will see you on Wednesday. Bye.
Thank you.